Okay, hello. Today I'm presenting Vahan. I'm presenting for Implants Paper Club. If you are on YouTube, just search for Implant Paper Club. That's how you find us. Today we are going to talk about a paper from ICLR, which was mentioned as one of the award-winning or honorary mention for award-winning papers. It's a very theoretical paper, but a very cool one. Uh, the title is Towards Understanding Ensemble, Knowledge Distillation and Self-Distillation in Deep Learning. Uh, all of these are related topics, and we'll develop theory to explain why ensembling works and when does it work. Same with why knowledge distillation after ensembling also works and when, and why self-distillation works, which is a cool idea, but we'll look at the self-distillation as well. I think self-distillation is not covered in detail in this short paper, but we'll mention the results. Right. So, quick view of the overall paper. Let's call it abstract. So we are going to develop theory to explain or actually quantify when ensembling improves model performance. Obviously, we have some assumptions, some simplifications for the model, for the training algorithm, for the optimization algorithm to build theory, but those are not too restrictive. And the result will be that ensembling even the same model trained with different seeds. Right? That's the theory. We don't have different models, different data or whatever. It's the same model trained on the same data, uh, but multiple times with different initializing seeds, and then ensembling those. Ensembling in a very simple way. We just average the softmax outputs. So here we will look at the classification problems. Ensembling helps to improve model performance. Uh, and then we also have theory quantifying how by how much. It's a probabilistic theory, but it should be good enough to show. So in this paper, there are no experiments. So the experiments are given in the longer version in the archive paper up here. We can go look at them later if you want, but really experiments are just to show the theory. Right? So there is no classical beating state-of-the-art sort of experiment. This is a very theoretical paper. Okay. Um, I guess before we continue, I also should mention this multi-view idea. So this is when uh, ensembles improve performance. So multi-view means when you train a model, there are multiple features that help detect or help classify the input vector correctly. Right? For example, if you have a car, to classify, there are multiple parts of the image that can classify the car correctly as a car. That's what multi-view means. And this is the only setup when ensembles work. We'll talk more about this later. Uh, we also will speak about the knowledge distillation. This is Hinton's work from 2015. Basically, after training an ensemble, you can train a distilled model, which basically learns to match the output from the ensemble. So you end up with a single model, which is more efficient, and you don't lose any performance compared to the ensemble. And ensembles improve the performance compared to each individual model in the ensemble. Okay? That's the whole point here. Any questions? I can't see you. So if there is anything, just speak out.
No questions so far.
Cool. So ensembles have a long history. You can see a couple of citations here. Again, there are more in the main paper, but it's a well-studied theory. You train multiple models, combine the outputs. So this is a very broad statement because you can do it in many different ways. You can train different models by having the same architecture, same data, or you can have different architectures, or you can have different data. They all work, in generally speaking, to improve performance on test set, right? Because here we will also assume that training actually converges, which means that on the training set, we have 100% accuracy, right? This theory assumes that, but it's also true in many cases for image problems, right? If it's a well-studied problem, you would be able, actually in general, you would be able to overfit the training set. The question is, can we improve the performance on the test set? Okay, using ensembles. So a few methods from ensembles. Well, boosting. So this is one popular ensembling method, which basically takes the coefficients, takes combinations of the coefficients from each model. Okay, that's and you train on those. Right, so you don't simply average, which is what we do in this paper, but in boosting, you also train on those coefficients from each model. There is also debugging and bootstrapping, where you would have different training data for each model. You can also combine different architectures. I don't know if there is much theory about that, but people do it in practice. And that seems to work well in practice. Obviously, developing theory with more variables is harder, right? And there is also the random having random forests where you have random features or decision trees. Here you kind of switch the features randomly, right, to create multiple models. Okay, those are the main ways of building ensembles. Here we will have the simplest one. Also, this is the author's claim is the first paper that studies ensembling the same architecture, same data with different seeds from a perspective where we assume we are dealing actually with a deep learning model. I'll show what they mean by that, because there is some theory when deep learning models, deep models are approximated as linear models with randomized features. Okay, but that doesn't really work with ensembles. So we'll look at that in a moment. There is a nice thought experiment with that. Now, the main claims in this paper. Now, training average does not work. What this means is that as you train, can you average the results, the output from each model during training, and use that as a model? So this doesn't work. You need individually, separately trained models, and then you average them at test time. You average the outputs at test time. It's important that these models are separately trained. Knowledge distillation works. As I mentioned, after having an ensemble, you can train a new distilled model, which basically distills knowledge into a single model from the ensemble. And this works. This doesn't lose performance, generally speaking, compared to ensembles. Okay? So there's this nice diagram here.
Question.
Go ahead.
When we speak of performance, what sort of measures are we looking at here, right? So
Accuracy.
it's just accuracy. It's not like say probabilities or something, because I remember that there were some differences where it matters whether it's accuracy or probability.
Probability, do you mean the logits?
For example, yeah.
Right. So no, we won't look at calibration or prior score, this sort of methods. It's just accuracy.
Okay, thank you.
Yeah. And we will use the logits to develop the theory, because that's how you create the ensemble, right? You take the logits after the softmax, and then average them.
Yes, yeah, makes sense. You could, in principle, also do the average of the predictions, right?
Yeah. Now here we take the logits after softmax, but not the argmax.
Yeah. Okay. Sure.
Cool. Oh yeah, and the third point, I mentioned this also. that self-distillation works. Again, we will have theory showing that self-distillation works, as in it has same sort of performance as an ensemble. The distilled model has the same sort of performance as an ensemble. Obviously, the mathematical definitions make things a bit not as simple, right? There are some assumptions, things are probabilistic, and there are variables, coefficients, and so on. But that's fine. That's how math works. So they have this diagram here, figure 1, showing how deep learning models compare with this random feature mappings approach. One of them is called neural tangent kernel. Actually, to explain that, let me scroll down here, find the actual formula. Here. Let me find that. I need to find the definition. It's a linear approximation. Here.
Wasn't it something where I think we had a paper on that years ago.
Yeah, possibly.
I think the idea was that if your layers get wider and wider and wider and are essentially randomly initialized, they approximate some kind of covariance function. And I think use these, you can sort of show that these are exactly as powerful as a neural network in the wide settings.
Yeah. So basically, this an NTK kernel. It's a feature mapping based on the original weights, the randomly initialized weights, that randomizes features X, right? And it creates a linear approximation for F. F is the neural network. W are the weights. X is the feature. Linear in W, right? Which basically converts the deep, highly nonlinear model into a linear approximation by creating randomized features, right? So you kind of change this X to become a randomized version. Okay, so which is why you can find an approximation, linear approximation for the deep model, and then we will argue that this doesn't work to explain to explain the why ensembles work and why distillation works and so on. Okay, but we'll come to it later. I just wanted to show this diagram here. Oh, yeah. Okay. And what we find from experiments is that first of all, let's look at the deep learning, the bottom line. This one is maybe more straightforward, right? Ensembling over 10 models performs about the same. So these are test accuracies. We assume that all models achieve close to 100% training accuracy. So those are ResNets trained on Cypher 10. Okay? So 10 ensembles with its knowledge distillation has the best performance on test data. They are very similar. They do better than training the average of 10 models, which is very similar to each individual model. Right? The point is that training the average of 10 models doesn't actually improve much when you have an actual deep learning model. Okay? But then, when we have these NTK random feature mappings with a linear approximation for the deep learning model, things kind of switch. So we end up having a system when training the average of 10 models is the best performing model, even though it's so much worse than normal deep learning models, right? I mean, the test accuracies are so much lower here. But what's more important is the sequence, right? Is that training the average of 10 is better than ensembling which is still better than individual models. And knowledge distillation is so much worse. Right? So if you and self distillation as well. So if you distill that, actually no, knowledge distillation is similar to individual models. Right? So which means when you ensemble and then distill, you don't keep the performance from ensembles. And then if you distill the individual models, which is what self distillation is, you lose performance. Right? So this linearized modeling doesn't work. So we need to develop theory, a new theory, to explain and understand why ensembling, knowledge distillation, both work. Okay, that's the whole point of this paper.
One quick question.
Yeah.
You mentioned that the training of the models has to be overfit. Does it have to be overfit, or is it just that the models should, in principle, be allowed to overfit?
Well, define overfit. I just meant that training accuracy should be close to 100%.
Yeah, so that would be overfit, right? So we would want. So if there was noise in the data, we want those ensembles to sort of be predictive of the noise, and then we sort of have the hope that in whatever distillation process we use, that sort of gets cut out.
Yeah, so in this case we do, but I suspect it's because so if you have training accuracy 100%, test accuracy 96, 97, is it really overfitting? It's kind of normal, right?
Yeah.
If you can, if each model can hit only 70% test accuracy, maybe things are different then, right?
Yeah.
But here, at least in theory, we assume that the training process achieves close to 100% performance accuracy, right? So in practice, if you can't have such high test performances, I actually don't know what will happen. They don't cover it here.
Yeah.
That's why I don't really want to call this overfitting, because test performance is also very high.
Yeah, it's hard to say then whether it's necessary or not. Yeah, cool. Thanks.
Yeah, exactly. But that's a very good point. Cool. I think I explained the theoretical questions. Right. They also speak about training accuracy 100%. Yes, training accuracy is 100%, and then self distillation still works in terms of improving test performance. Okay, so those are the questions we will ask. Another important thing that we will cover is multi-view. I mentioned this, but basically it means there are more than one features. There are data points in the training set with more than one features that can accurately predict the correct class. Okay, I think that's what it means. There is a lot of notation. I think they reached, well, not I think, they actually reached to, they use so many Greek letters that one of them I didn't know how to pronounce. So when we get there, I may ask for your help. So we will also use this omega. If you are not familiar with it, this is basically an asymptotic. This is an asymptotic lower bound. Right? Big O is an asymptotic higher bound. Omega is a lower bound. And we will need lower bounds here because we will have a negative exponent, negative value of an exponent. The tilde represents log polynomials. So this is an asymptotic lower bound on a polynomial of log items. Like log square would be one example here. We'll see what it is in a moment. I just want to cover the notation as we go. Okay, I think that's the main thing. We will use gradient descent for theory because I suppose we don't want to add extra probabilities due to stochastic gradient descent or even the momentum method. Just things make the theory even more complicated. So we will assume it's a gradient descent. Let's make sure I don't miss anything important. Okay, there are experiments as I mentioned in the main paper, which is not here, there are a few tables. If you go find the paper in the archive, here it is one example. Lots of experiments with a few main points. So knowledge distillation does not work for random feature mappings. They run lots of experiments to show that. Special structures in the data, like multi-view structures, is needed for ensembles and neural networks to work. Right? So without multi-view structure, ensembles won't work. It's also important and empirically observed. There is another interesting observation here. There has been theory that that the variance due to label noise and the non-convex landscape of training because of the non-linearities in the model. Was there a hand or question?
Peter, this is a drop.
Okay, that's fine.
Yeah.
I just can't see the video. Sorry about that. The variance due to label noise or the non-convexities in the training landscape in each model may not be connected to the superior performance of ensembles, right? So there has been theory that suggested maybe ensembles do better because of the label noise or non-convexities in the training landscape, but that doesn't seem to be the case. Okay, based on the experiments. Cool. Any comments before we continue with a couple of simplified cases? Okay. As I said, this linearized random feature mappings doesn't work. Basically, they run a simplified example. First of all, a few contradictions, right, that we can see. So if you have this linearized random feature mapping model described here, we find a couple of contradictions. The training average works even better. As I said, as I showed in the diagram before, turns out if you average the output of each model during training and then train like that, it actually works better. That improves individual model performances. But that's strange because it does not improve the test accuracy. Okay, because that's why we assume that it's the improvement comes because of the larger set of random features. Because as we combine the outputs during training, we are effectively increasing the set of random features, which helps. So that's one theory. But this is not the case for deep models. There is one difference here. The other one is that knowledge distillation does not work, which is also interesting because if we use the NTK feature mappings, train ensembles, and then distill the ensemble model, the performance gets worse, which suggests that decreases the performance on test models, right? Which suggests that the feature space gets enlarged during training, right? Because we are basically overfitting to the training features, but we are not able to use that information for test time. Okay. Any comments here? I'm trying to explain, but I'm not sure if I'm doing a good job.
Might be a bit of a stupid question, but in the distillation process, how did that work again? And do we need extra data to do that?
No, so the distillation, basically, not a stupid question, it's an important question. So this distillation, you do it after you train all models in the ensemble, right?
Mhm.
And then you train a new model that tries to match the result from on the same data. So
On,
I
on the
think
training data, yeah.
I think it's the same data. Yes, same data, because you're trying to match the output from the ensemble into the new model. Right? You want to make sure that your new model predicts the same thing as the ensemble.
Yeah.
So it's the same data. Yeah.
So you wouldn't do that on like some kind of calibration or holdout set or so.
How would you do that? Maybe you can. Maybe you can, right?
In principle, yes, but
Yeah, I think you can. Why not? I don't think actually. Yeah.
I was just wondering. So during distillation,
Hmm?
would you still care about not overfitting? Because if you essentially trying to
Hmm.
mimic the ensemble in an existing in a single model, do you still care about overfitting?
I think no, because you're trying to uh, compress weights from 10 different models into one model, right? So if the original ensemble overfits, this will still overfit. If it doesn't, this won't. That's my
Okay, makes
understanding.
sense.
But obviously, there is a lot of theory that does other things with the distillation. It's like this was the distillation was published in 2015, so many things happened since then.
so if all models would be overfitting, wouldn't then also the prediction of each input point be essentially the correct label on that data point? Wouldn't the distilled model not just train the same? Say if you have 10 models, but all are overfit, and say that you have the same data point in that distillation process, wouldn't they all have the same target, and so the distillation would also have a high chance of overfitting, or was there some way of
Yeah, it's a very good point because they call it that is dark knowledge. I think this is where it's going, right? Because they're asking the same question. They're like, okay, how does this then work, right?
Mhm.
Where is that dark knowledge? They call it dark knowledge, hidden in the output of the ensemble.
especially when you think of like self-distillation, where
Yeah, exactly, right? How does it even? How is it possible?
yeah.
So the answer is it's in the soft labels, which is the logits after the last softmax, the softmax, but before, not the hard labels, not doing argmax. That's what they call lost soft label. So there is information there that helps. So if we average the soft labels, there is knowledge there. That's the answer, short answer. There is more theory which we can try to understand here, but I think the answer is that because there is information in the soft labels, we don't actually lose performance.
So does that mean that the argmax at the end, in some ways, loses some information?
Obviously, it does, right? Because if you look at the logits, right, you actually have each probability, right? For each pin you have a probability. I mean, maybe I shouldn't call it probability, but people call it probability. When you do argmax, you only take the maximum bin. Right? You forget about everything else. You don't know how much uncertainty there was. You don't know the confidence levels and so on. So yes, you lose information.
But yeah, but if
Okay.
they are all overfit, wouldn't you also expect the logits to be, say, clustered on some fairly high or low prediction? And yeah,
I don't know. Maybe. Uh, so maybe. I don't know. They don't really
perhaps
cover any
I think that
details.
might be why the different features are so necessary. That fundamentally some of the the trained models have fundamentally different performance characteristics.
Yes. Okay, since we spoke about features, let's actually go to the longer paper, which is 73 pages, right? So there's a lot of stuff in here. So let me find that one diagram that shows the feature extraction in a hidden layer. So there is this one. Okay, so first of all, this image. This one is also in the published paper. So if you have a car, multi-view means you can use the windshield, the headlights, the wheels to detect it's a car, right? So a single view would be if there is only one feature that can detect the car. Now, what happens when you train ensembles? There's this large here, this one. Is that each model, so this is taken from layer 23, from ResNet 34, right? One of the hidden layers. What you can see is that, so I think they're not very explicit here, but I think each row, no, each column represents a different model, and each row represents a different image, right? You can see that. So for the same image, these are different model outputs from different models. And you can see that each model is paying attention to different features, right? Is learning different features. So they call it a feature learning process. So that's how they explain why ensembles work, because each of the models is learning a different feature, and that may only make sense. That's only possible if you have this multi-view data, right? If you have only one feature that can describe the model, then ensembles don't make sense. But if you have data where multiple features can accurately predict the class, then each model, because of random initializations, each model in the ensemble learns a different feature, right, for the same image, which is how the extra information and then is kept in the soft layers at the end, soft labels at the end. It's kind of carried across there. I don't know what the labels would look like because of multi-viewness of the data. Right? I can't really describe what would there be more uncertainty? Would the logis be more flat and multimodal, whatever? I really don't know that. But what we do know is that there is information in the labels that gets carried across from hidden layers, which learn different features. Does this answer the questions? Yeah, I'll take the silence as a sign to continue.
Yeah, makes sense.
Yeah. Cool. We spoke about this feature learning process, right? That image kind of shows how feature learning progresses. All right. So they also say that previous work often studies cases when the input distribution is Gaussian, but that's not exactly true. But they want to understand training accuracy, and at the end of training is 100%. Okay? It's just an assumption in the theorems. So they have a few examples with this multi-view data, but to be honest, I kind of find this a bit confusing. But basically, this V1, V2, V3, V4 are 4 features. V1 and 2 correspond to the first class label, V3 and 4 to the second class label. Now we have a binary classification setup. Just a small example to show what multi-view means. Now, now in the data distribution, when the label is class 1, we have class 1 and class 2. Right? When the label is class 1, then both V1 and V2 appear with weight 1 80% of the time. V3 and V4, only one of them, right, appears with weight 0.1. And then if only V1 has weight 1 or only V2 has a weight 1, then probability is 10%. So like it's very likely that V1 and V2 appear together with weight 1. This basically means both V1 and V2 can help to accurately predict the data point. Right? There are features that accurately predict the data point. It's just an example with the numbers here. Same with class 2. But here, V3 and V4 predict class 2. Okay? This is what multi-view would mean. Okay. Continue. How individual neural networks learn, right? So when we train an individual neural network, each of them learns, as we saw also from the hidden layers. Each of them learns feature mappings, right? Learns a feature to correctly predict the end. But depending on the random initialization, the learned feature can be different because of the multi-view data. So the most accuracy is learned from those main features, and then the rest is really memorized, which is why the test accuracy would remain 90%, right? Even though training is 100%, because that extra 10% is gained from memorization, and it doesn't generalize. On the other hand, when you have an ensemble, because each model learns a different feature, generalization can actually, the test performance can get higher because that extra 10% memorized gets kind of overridden by the other model. I'm trying to give a high-level explanation of what's going on here because I found this part a little bit confusing, but I think this is what it meant. Because the model here, this sentence I think is important. Hence, by training the individual model to match the output of the ensemble, this is about the distillation. The individual model is forced to learn both features, even though it has already perfectly classified the training data, right? So even if the training data is now overfit, model still has to continue learning because this is about distillation. Because it has to match every separate model. That's why distillation also works. Was there a comment?
Yeah, I was wondering. So during distillation, I'm not too sure how distillation works in practice, but in my mind, it's almost like just using back propagation to match the outputs of that ensemble, right?
Yeah, pretty much.
So I wonder if doesn't that then get the process of focusing on 90% versus the 10% memorization, doesn't that happen during distillation as well?
No, this is what this sentence was, right? Because the different models learn from different features to predict the same data point. During distillation, the model is forced to learn both features, V3 and V4. Otherwise, it would learn only one of them because one of them is enough to predict the class. But now it has to learn both of them. Right? So basically, because let's say you have two models, right? One of them learns V3, the other one learns V4, right? But then during distillation, what happens is because you're trying to match the output from the model, from the ensemble, the distilled model has to learn both features. So basically, it learns more features than individual models, because the individual model can learn one of them and get away with high training accuracy.
Oh, I see. And this is because it's looking at the soft labels and not the hard labels.
Exactly.
Okay, that makes a lot of sense.
That's what I said. There is dark knowledge hidden in the output of the ensemble model, which is in the soft labels. Yes. Yeah. A bit of the importance of this technique, because it's a framework of they introduce a generic framework of feature learning, right? How learning features happens during ensembling and distillation afterwards. This is a visualization of the features with no noise also, but I don't think this is very important. We have very little time, so I would rather continue. So it's interesting. So when they develop the actual theory, they have to give specific values to all these parameters. I'll explain what these are, but they also argue that this is just to make the theory a bit smoother, but a lot of these can be generalized to many other values. But I like how they simplify many things to develop the theory, which later can be extended and is extended in the main paper. Right. A bit of notation. There are a few assumptions here actually. So when we say with high probability, this means a probability at least 1 minus exponent of negative lower asymptotic bound on log square k. K is the number of classes. It's a classification problem. Basically, if you have 100 classes, this is already very close to 1. If you have 1,000 classes, this is basically 1. On the other hand, 1,000 classes can be a lot, right? They also argue that you can have much fewer classes, but that would require more features. There is a trade-off here. And the theory can be developed either way, either higher number of features or a higher number of classes. But that makes sense, because if you have 2 classes and 2 features and lots of points and lots of data points, then you may not have enough information to train a model, right? Because your problem becomes very much under what's it called, underdefined, right? So you need to either have many classes or many features. I think that's fine. They also assume that feature vectors. Now we assume there are only 2 feature vectors, 1 and 2. Those are for each class there are 2 feature vectors. Those are orthogonal. Again, it can be extended to what they call an incoherent case. They say trivially. Obviously, I haven't seen the proofs, but that's a trust assumption. So this assumption will help with the theory. Fine, as long as it's extendable, you shouldn't worry too much. V is the set of all features. Fine. We'll have a few more definitions. We have data distributions for the multi-view and single view. And basically, we will assume that we have a certain amount of multi-view data points in the distribution. Right? It's not all multi-view, but there has to be a significant amount of multi-view data. Any comments? I'm taking a pause, maybe. Okay. Some more definitions. You don't have to cover all of them. The big gamma, I wasn't sure what this was. I actually didn't find where it was defined. But it doesn't matter too much, because basically we define this defines how data is sampled from each multi-view and single view data points. Okay. Basically, we have a feature vector XP. Z is a coefficient satisfying one of it's sampled from here, depending on if it's a multi-view or single view. It's sampled either one way. There is also noise. The edit noise. They don't actually have any assumptions about noise. Actually, they any limiting assumptions. So there is noise in the features. Fine. And they say so P is the distribution from where we sample the data points. This calligraphic P is the distribution from where we sample coefficients. ZP, I think. Yeah. I think we can scroll down here a little bit and can should we just look at the results, because they also define, oh, this is the smooth ReLU. Fair enough, they use the smooth ReLU because we need to work with gradients. I didn't know how to pronounce this letter, but doesn't matter too much. It's a threshold that defines where you smooth the ReLU, right? It's like instead of cutting, you have a little smoothing thing down there just so we can calculate gradients. Oh, they also talk about over parameterization. So we will choose this parameter M, which is a log polynomial, so polynomial of logs of number of classes. So it's in a range, right? So we can choose to have many features. So if M is closer to K, then we have a higher, larger number of features. So if it's closer to poly K, so it's like it's a log polynomial. It's a polynomial of logs, so it's much lower, and it basically helps the theory a bit more convenient. Okay, all this notation gets a little bit convoluted eventually, but basically what we really care about is right. So this is the logit. We mentioned the logits, right? This is the softmax function, and we will use that for our theory. So lots of definitions there. I didn't want to cover every little thing because I might also make a mistake, because it's important to find every letter. I just try to cover the important ones. And we have the loss function, which is cross entropy loss, and it's a two-layer network. I didn't mention that before. Now we study only two-layer networks because we want a limited number of sums, right? It's a sum of sums. Actually, if you go up here, you can find here. There's the loss function. There's the network, right? So 2 layers. W's are the weights, X are the features with the ReLU. Okay? This is our network, and we have a loss function, which is defined with the cross entropy loss. Okay, the rest is standard. Now, two main theorems. Before that, any comments? Okay. If you have a single model, we make the following assumptions. The model, for every significantly large K, right? So as I said, we assume large number of classes, which defines the probabilities. And for every M is given in this range, and every eta, which is also bounded by a polynomial of K. I think we choose like 1 over K squared here. We train a single model using gradient descent. Has to be gradient descent for the theory to work, starting from random initializations, as we defined before. Then after 3 iterations, so it's iterations are a polynomial of a number of classes, eta is the coefficient. With a high probability, this is the high probability we defined before, the model F satisfies. The training is perfect, so we can perfectly fit the training set. So this means that for all x and y in the training set, that is the training set. For all classes, each fitted model, Fi are the fitted models, are lower. The loss is lower than the Fy, which is the forward pass. This is just a forward pass if you give x as an input. So we can feed the training set perfectly. But the test accuracy is bad, consistently bad. This is the more useful part, right? More interesting part. So this basically means the opposite sign here. This basically means that with a probability about half mu. So mu is a parameter we choose, right? About half mu, like just left and right from mu. Not much lower, not much higher, right? So the both bounds, there is a tight bound here. The performance is bad. Okay, so for test time, we cannot get very close to the best possible value. Okay, with a high probability. That's the bad news about a single model. This basically means a single model is not able to generalize well enough. So here there is funny because now we have only two feature vectors, 2 features per class. We can, if one is L, the other is 3 minus L. Right? It took me some time to understand what this was, but it's interesting because we have only 1 or 2. The other one is 3 minus 1 or 3 minus 2. So this is basically a way to talk about the other feature in the multi-view setup. Anyway. And in terms of ensembles, now the better theorem. So when we have an ensemble of models, right? So L represents the ensemble number. We have a similar theorem which says training is still perfect for the ensemble, right? So we train each model, and then the ensemble on the training set is perfectly fit, and the test accuracy is upper bounded by a very small mu. Remember, it was like 0.5 mu. Now it's like 0.01 mu. This is good news, right? So there is a theory showing there is significant improvement in test accuracy from an ensemble. Okay? This is the probability. This is the probability of performing badly, which is very low. This is what it means. Right? The probability of performing badly is very low on the test set. Okay, and knowledge distillation. So here, for knowledge distillation, they use this a version from logit function, but the temperature version. So there is this temperature scaling here, which is slightly different from the original distillation, but it's the same thing. They use it to make theory nicer, because that way we can calculate the gradients and so on. But the point is, important point is that the last theorem, distillation algorithm results in with a few coefficients after a few iterations, with probability of at least very high probability, right? Same high probability for at least 90% of iterations t, the following holds, right? So this 90% is a bit interesting. I didn't understand the reasoning behind it, but I guess theory shows that. So it's not for all iterations, right? So when you do distillation, you should know when to stop training, because not for all iterations that good results hold. Training is still perfect. Test accuracy is almost perfect. Same result as for ensembles. This is the same bound. Okay, but it's not for all iterations. It's, as I said, for 90% of iterations, which I think is fine. Okay. That's it. No conclusions, nothing. They could barely fit under the 9-page limit. And we end with this theorem. Any comments? Okay, I'll stop recording.
Yeah, it was a very interesting